You are interested in wind farms, huh? I bet you drove by one of them 1,000 times, and the last time you drove by you asked yourself, how the F do they work? Or you are here because of a school project and you need to learn how they work. In any case, I hope you enjoy the video and learn something now out of it. Wind power plants, also known as wind farms, are installations of wind turbines that convert kinetic energy from the wind into electrical power. They are a renewable energy source and an important means of reducing dependency on fossil fuels. Here's a brief rundown of how they work. Wind turbine components. Each wind turbine consists of a tower, a nacelle, the box-like structure at the top of the tower, and rotor blades. The nacelle houses the key components like the generator and gearbox. The blades are designed to capture kinetic energy from the wind. Energy capture and conversion. As the wind blows, it passes over the blades, causing them to lift and spin. This spinning motion turns a shaft connected to a gearbox in the nacelle, which increases the speed of rotation. Electricity generation. The high-speed rotation of the shaft from the gearbox is transferred to a generator. The generator uses the principles of electromagnetism to convert this mechanical energy into electrical energy. Power to the grid. The electricity generated is then sent through transmission and distribution lines to homes, businesses, and other entities that use electricity. Now that's it for this video. I hope you enjoyed. Ha 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 ha. I'm joking. Let's dive in a little deeper and explain everything a little better. Wind turbine components. Blades. Wind turbine blades are airfoil shaped to enable lift from the wind that makes them turn. The materials used to make the blades need to be very strong and lightweight. Typically, a combination of lightweight, durable materials like fiberglass and carbon fiber are used. The length of the blades varies depending on the turbine size, with larger turbines having longer blades to capture more wind energy. Rotor. The rotor is the part of the wind turbine that spins when the wind blows. It consists of the turbine blades and the hub, the central part to which the blades are attached. Nacelle. The nacelle is the large structure sitting atop the tower, housing all the key components for electricity generation, such as the gearbox, generator, and control systems. Gearbox. The gearbox is designed to convert the low-speed rotation of the rotating blades into a higher speed rotation that is suitable for the generator. Some newer models of wind turbines, however, utilize a direct drive mechanism that omits the need for a gearbox. Generator. The generator is where the conversion of mechanical energy, the turning motion, into electrical energy occurs. Most wind turbines use an electromagnetic generator to accomplish this. Tower. The tower supports the nacelle and rotor and elevates them to a height where the wind is stronger and less turbulent. Towers can be tubular steel, lattice, or concrete, and their height can range widely depending on the size of the turbine and the characteristics of the wind at the site. Yaw mechanism. The yaw mechanism rotates the nacelle so the rotor faces into the wind to capture as much energy as possible. This is essential because the direction of the wind can change, and the turbine needs to adjust accordingly. Anemometer and wind vane. These devices are used to measure the wind speed and direction, respectively. They send signals to the control system to optimize the turbine's operations based on wind conditions. Brake. Wind turbines have braking systems to halt the operation of the turbines under certain conditions, such as excessive wind speeds that could cause damage. Control system. The control system operates the turbine's functions, adjusting the blade angles, orienting the turbine into the wind, and shutting down the turbine when necessary to prevent damage. These components collectively allow wind turbines to efficiently capture wind energy and convert it into usable electrical power. Energy capture and conversion. Energy capture. The process starts when the wind blows over the blades of the turbine, causing them to lift and spin. The design of the blades, similar to the airfoil design of airplane wings, allows them to capture the maximum amount of wind energy. The speed at which the rotor turns depends on the wind speed and the design of the blades. Conversion to mechanical energy. The spinning of the blades is a form of mechanical energy. This rotational energy is transferred down a shaft in the nacelle to the gearbox, if the turbine has one. Gearbox. In turbines with a gearbox, the gearbox's role is to increase the rotational speed. The slow speed of the blades is not sufficient for electricity generation, so the gearbox increases this speed before it reaches the generator. Some modern wind turbines, however, use direct drive generators that eliminate the need for a gearbox. Conversion to electrical energy. The generator takes the high-speed rotational mechanical energy and converts it into electrical energy. This is typically done using electromagnetic induction, where the rotation of the shaft induces a magnetic field in the generator, creating electrical current. Power electronics. Once the electricity is generated, power electronics ensure the electricity is suitable for the grid. They convert the raw, fluctuating power that comes from the generator into a form that matches the grid's requirements in terms of frequency and voltage. Distribution. The electricity is then sent down the tower, where it may be stepped up in voltage by a transformer before it's distributed into the electric grid and ultimately to end users. Wind turbines are designed to operate efficiently over a range of wind speeds. They have a cut-in wind speed, below which there's not enough wind power to overcome the resistance of the generator, and a cut-out wind speed, above which the turbine must be shut down to avoid damage. In between these, they have a rated wind speed, at which the turbine produces power at its rated capacity. Through the combined processes of energy capture and conversion, wind turbines harness the power of the wind to generate clean, renewable energy. Electricity generation. Electricity generation in a wind turbine occurs in the generator, a key component located within the nacelle. The basic principle used here is electromagnetic induction, which is the production of an electric current across a conductor moving through a magnetic field. The principle of electromagnetic induction was discovered by Michael Faraday in the early 19th century. Here's how the process works in a wind turbine. Mechanical energy. When the wind blows, it turns the turbine's blades. This rotational movement is a form of mechanical energy. It turns a shaft that leads from the hub of the rotor into the generator. In many wind turbines, a gearbox is used to increase this rotation speed, as the generator requires a faster rotation to operate effectively. Electromagnetic induction. Inside the generator, the rotating shaft turns a rotor, which is basically a series of magnets, around a stator, which consists of coils of wire or conductors. As the rotor spins, it creates a changing magnetic field around the stator. This changing magnetic field induces a flow of electric current in the stator, the principle of electromagnetic induction. Conversion to electricity. The movement of electric charges, electrons, constitutes an electric current, which is harnessed as electricity. However, the raw electricity produced by the generator may not be suitable for immediate use or distribution. It may be fluctuating or not at the right voltage or frequency. Conditioning of electricity. This is where power electronics come into play. They condition the raw power into a form that matches the requirements of the grid, typically converting it from alternating current, AC, to direct current, DC, then back to AC at the right voltage and frequency. Transmission and distribution. The conditioned electricity is then sent down the tower, and in many cases, a transformer steps up the voltage for more efficient transmission over long distances. From there, it is distributed through the power grid and eventually used by consumers. This whole process happens continuously and simultaneously as long as the wind is blowing at the necessary speeds, allowing for the conversion of the kinetic energy of the wind into usable electrical energy. Power to the grid. Once electricity is generated in a wind turbine, it's crucial to get this power to the end consumers. This is done through a system known as the power grid, which is a complex network that connects power producers to consumers. Conditioning and transformation. As mentioned earlier, after electricity is generated in the wind turbine, power electronics ensure the electricity is suitable for the grid by converting it into a form that matches the grid's requirements in terms of frequency and voltage. In addition, the voltage of the generated electricity is typically stepped up by a transformer for transmission. This is done because higher voltage electricity can be transmitted more efficiently over long distances, reducing energy losses. Transmission lines. The high voltage electricity is sent through transmission lines, which are large, high-capacity cables often strung between tall towers. These lines carry electricity over long distances from the power generation sites to more populated areas. Substations. Substations are part of the electrical grid infrastructure that performs several key functions, one of which is to step down the high-voltage electricity to a lower voltage more suitable for local distribution. Distribution lines. After the voltage is stepped down at the substation, the electricity is distributed to homes, businesses, and other entities through a network of smaller power lines, known as distribution lines. Consumers. Finally, before entering your home, another transformer, often seen on a power pole or in a green box at ground level in some neighborhoods, steps down the voltage further to a safe level for household use. Once it enters your home, it's distributed through your home's internal wiring to outlets where you can use it to power appliances, charge devices, and more. It's worth mentioning that the power grid is a two-way system. While it distributes electricity from power plants to consumers, it can also carry electricity in the other direction. For example, homes with solar panels often generate more electricity than they need during the day, and this excess power can be sent back to the grid for use elsewhere. The entire system, from wind power generation to grid distribution, requires careful management and coordination to ensure the supply of electricity meets demand in real time, and that the integrity and stability of the grid are maintained. Grid operators constantly monitor and control the grid to ensure this balance and to quickly respond to any issues that arise. Wind power plants can be located on land, onshore wind farms, or at sea, offshore wind farms. Offshore wind farms often generate more power than onshore ones due to more consistent and stronger winds, but they also come with higher installation and maintenance costs. The size and capacity of wind power plants can vary greatly, from small installations that provide local power to huge farms that provide power to entire regions. Wind power is considered clean energy because it doesn't produce emissions during operation. However, like all forms of energy, it has environmental impacts including noise and visual impact, and potential effects on local wildlife. Ongoing research and technology improvements aim to mitigate these impacts. Well, this was everything for today's video. Please consider subscribing, leaving a like and commenting on the video since it helps the channel grow. Thank you for watching and see you next time.